Hey, what's going on, guys? So, just as the homogeneity of space leads to the conservation of linear momentum in classical mechanics via Noether's theorem, conservation laws, for a given transformation to be zero, the isotropy of space, right, equivalence of all directions, leads to the conservation of angular momentum as well. Okay, just in the same way that we have a translation, some translation in space. Looks like this. If we were to rotate the laws, basically the system in space, it should also, the laws of physics should be the same. We just might pick up some more complicated terms, like the Coriolis force, etc., that are kind of fictitious, but require momentum to be conserved. So, let's say an infinitesimal rotation of a system as a whole by some angle. I guess let's just call it. This is just a little. This would be a little angle that we're going to call d phi, just to rotate the system incrementally, okay? And we change the radius vector a for each particle to Ra plus del r sub a, kind of like we did with the translation operator, where d by Ra is equal to del phi cross product with Ra, okay? And so the operator for this transformation, we can just call this the R rotation operator, which is associated to that little rotation. We'll define this as 1 plus del phi, the magnitude of how much we're rotating that little guy, with a dot product of the sum, okay, over all the all the eighth components of the particle or I guess all the system, basically, with respect to the gradient for all of those A particles. Okay, so we have a continuum of particles that we can, or I guess just a couple of vectors that are pointing out that represent different particles, and we're rotating the whole system. Okay, so remember, for the Hamiltonian of the closed system to be invariant under rotation, it must commute with the rotation operator. Okay, so it must compute with this thing that we'll call the generator of the rotations. So this is the generator of rotations. It's just simply the cross product of the vectors of all those particles, cross product with their corresponding pseudovectors. So what we should have then is that the conserved quantity of the total angular momentum of the system should look like, for a single particle to be defined in units of h bar. So let's say the angular momentum operator, let's call it L. Let's do a cursive L so it's not confusing. It should be, it should look like R cross p hat. Okay, so the location of particle over the vector crossed with the p hat operator. And so we'll define it in such a way that we have R cross nabla. All right? In units, this is in units of h bar, right? All right, we're assuming this. So in our Cartesian coordinates, let's just restrict ourselves to this. We have, L sub x will be y hat cross pz times pz minus the z hat operator acting on the this would be the y. So it's always, we're switching kind of the indices here. You have this crisscross between the y and the z's. Okay, that's kind of an aside, but that's typically how I thought of the cross product. But we'll have that this should be the negative I of, with respect to sorry, I'm really messing this up. Y with the partials in the z minus z with the partial in the y, okay? And then for the L sub y, it should be actually z with the px, these are all operators, by the way, sorry, minus the x with the pz, which then looks like I, and I do recommend, writing this all out so you have some practice. Okay, and then the last one would be L with the z, and this should be given as x first, okay? with p hat minus y hat px. Okay, this is all in the z direction. And this should give us negative I times the quantity of this x del by del y minus y del by del x. Okay, and so the operator for the total momentum, the operator for the total momentum of particles, or total angular momentum of particles, sorry, would be L hat, capital L hat, which is going to be defined as the sum over all the eighth particles, okay, for these L components, and then for each of their x, y, z in space, we should have this. So it's a little bit complicated, but we can use this canonical kind of commutator relation to express this, right? So we can use this because of our defined quantum mechanics. Let's say the ith position component with the kth momentum component should be equal to ih bar times this Kronecker delta function. Okay? And so this Kronecker delta function is just going to pick out, let's set it equal to 0 if they commute, and set it equal to not 0 or 1 if it doesn't commute. Okay? This basically gives us our orthonormality kind of, this is we use this for our definition of orthonormality, but we can also use this for the commutation relations for the angular momentum operators. Okay, so it's a useful kind of mathematical tool. And so what we have here is that the x component, okay, or the x operator, or the angular momentum operator acting in the x for the system of particles, and the angular momentum operator for the y for a system of particles, would give us the I times the angular momentum in the z direction. And we can also have that the L component here, comma LZ hat, should give us ILX. Doesn't this look quite familiar in some way? We have this kind of this almost kind of let's see, LZ. Okay, then we get it in terms of the L hat sub y operator. Okay, so now we have these three results, and we can actually just instead, now that you've written all these out, we can write this in a shorter, or more shorthand version using something called the Levi-Civita tensor. Okay, the Levi-Civita tensor, and this is going to be epsilon of ijk, and so it's going to give us this property that we want and spit out whatever relation, whatever cyclical relation that we're getting, that we observed with this pattern. And sorry, this should be an I. So this would be I, comma j. We take the commutation between them. In general, it should be I times the Levi-Civita tensor times the angular momentum operator in the kth direction. Okay, and so this should really be a powerful kind of statement. But the non-commutativity of the angular momentum components is really a profound result. Okay, this is going to show that it is this basically all of this. Okay, so all of this implies, okay, this all implies that it's impossible to simultaneously know the precise values of more than one component of then more than one component of the angular momentum vector. Okay, so we can't know more than one component of the angular momentum vector, which is something that is limited by or is constricted in quantum mechanics. Okay, so this is a direct expression again of the uncertainty principle for angular variables. So if we measure L, Z precisely, okay, if we measure L sub Z precisely, Lx and Ly become they become fundamentally uncertain. We can't know anything about the other components. Okay, so this is very important. This is very important to recognize, because the operator for the square of the angular momentum, okay, if we were to square this, so let's say L hat Z squared, or X squared plus L hat Y squared plus L hat Z squared, okay? This commutes, this 2 M's, take my word for it. This commutes with electric components, okay? So we can have that the commutator between the angular momentum, which is supposed to be our invariant, right, with those particular components, but it commutes with this, okay, for x, y, and z. Okay, we know this. So that means that the magnitude of the angular momentum vector, represented by L hat squared, and one of its components, let's just say, I don't know, LZ, okay, one of its components, L sub z, and it's the hat, of course, because it's an operator, they can be simultaneously measured. So we can know the total, we can actually know the magnitude. So this is very important. We know the magnitude or I guess we can extrapolate the magnitude, right, of the angular momentum vector and know one of the components. But that's it. That's all nature will allow us to know. We can know one of its components in a direction, okay? In some direction, we can know some let's call it LZ, okay? Nature will allow us to know one component of the angular momentum vector, and it will allow us to know the magnitude, I guess, wherever the heck the other one's pointing, right? Which is, L hat X and L hat Y are going to be completely unknown, okay? Or their uncertainty is infinity, okay? We don't know anything about these, but we can know L hat squared, okay? That's very important, okay? We can know the final length, okay? I just want to make that very clear. And so in spherical coordinates, now let's look at spherical coordinates now. What this particularly means for a single particle, okay? It can take the form that the components of the angular momentum vector, let's say in the z hat direction, will be E or I by del phi, okay? So we can look at this operator here. And then, of course, next we have this strange kind of relation, which is that plus or minus L hat X times I L hat Y is equal to E to the plus or minus the phi coordinate, or the I guess this would be the not the polar coordinate, but the well, it is a polar coordinate, but there's the azimuthal and the polar angle. I think this is the azimuthal angle, but if we can, yeah, it is, because we can go around plus or minus, and so this would be plus or minus then. This would be plus or minus the polar angle plus cotangent theta, scaling that in front of the operator with the derivative of this, okay? And we can also have that the square, we can also know this for certain, the squared magnitude of the angular momentum vector, which is sine theta times the derivative with respect to theta, of course, with our form here, okay, plus 1/2, sorry, not 1/2, it's 1 over sine squared theta with a second order partial derivative with respect to phi, the azimuthal angle, okay? And so we can know this, and we can know a single component, of course, which would then give us the kind of plus or minus representation in terms of this, and yeah, this is all we can know, okay? So this is important to kind of try to delineate, okay, in this idea of quantum mechanics. It's very important to understand angular momentum because this is going to be responsible for a lot of our next results in three-dimensional Schrodinger equations and solving them. So let's look at a derivation of the angular momentum eigenvalues. So we're going to look at this algebraic method to derive these quantized. Well, first of all, we want to quantize the values of L hat squared, and let's just look at the z component because I can only know one using only their commutation relations. Two m's. That's basically what we want to do. We want to find the quantized eigenvalues of these two guys using only their commutation relations without ever solving a partial differential equation. This might seem kind of out of left field, but I think you're going to understand the importance of these the special linear properties that these operators have because we're translating these differential equations to just some basic algebra. Okay, and so this is inherently kind of a master class in this algebraic method. So let's look at the psi. Let's look at, we want to find the eigenfunctions for the angular momentum, and for some m to be simultaneous. Okay, we want these to be simultaneous eigenfunctions of L hat squared and of L sub z. This is very important because we need to set the conditions in this algebraic kind of representation for these eigenfunctions to give us these eigenvalues that we want. Okay, and we want these eigenvalues to come out naturally. Okay, so it looks something like this, and also it must satisfy this as well for the reading that we're getting on that one component of the angular momentum. And so we have this guy here, squared m is equal to capital M. Okay, this will be our m coefficient for the eigenvalues on the measured axis. Okay, so here's our eigenfunctions and our eigenvalues that we want, and they're quantized. So what we need to do is define something called the ladder operator. Okay, and so these are ladder operators. So let's look at ladder operators. They look like this, the form that kind of looked really strange earlier. But we have this plus or minus that's propagating this uncertainty in the other components that we don't know, right? The commutation relations between the other axes, right? The commutation relation between the axes that we know for sure and the other uncertain axes, we can create an algebra for this. That this should be plus or minus this ladder operator here, and so let's see how this guy, this like uncertainty, this operator of uncertainty, acts on. Let's see how it acts on psi m. So let's act on psi m. Okay, I want to suppress. Let's suppress the L squared label, okay? Okay, so we're just, this is the same, these are equivalent. We're just going to suppress this for a second, okay? Just bear with me. So we're going to have this algebra here, where we want to look at the plus or minus acting on psi m, okay? And of course we want psi m because we want the eigenvalues. So we have one can have this relation here. Those are equal to each other, and this will also be acting on psi m. And then what we would do is have this L hat plus or minus to be acting on LZ in terms of the angular momentum component we know here, plus or minus L plus or minus operator acting on psi capital M, okay? And this should give us some nice relation here, which is the plus or minus with the energy eigenvalues, the angular momentum eigenvalues, plus or minus L hat plus or minus the ladder operator, remember, is that. And so what we can then get from this, or what we can deduce, is that the eigenvalues, plus or minus 1, we factor this out, with this ladder operator basis, gives us, we should observe something like this, right? And what this is basically telling us is that this shows that the function, so this function here, the ladder operator acting on the basis, or the eigenbasis, or I guess eigenfunction basis, eigenbasis function, whatever, of that this is an eigenfunction of L sub of the this is an eigenfunction of this operator that we observed. And so with the eigenvalue raised or lowered by some particular unit, okay, so we raise it up or we lower it by some unit, and it's still an eigenfunction. It's still an eigenfunction of L hat Z. And so, you know, if we were to have a raising operator, we're going to define this as a raising operator. The raising operator. And we can define this guy as the lowering operator. Okay. This is we have the raising and lowering operators as an eigenfunction of exactly the state that we know for certain, okay, or the state that we measured, okay. Because remember, operators in general are in terms of what we raised and or in terms of what we measured, okay, in terms of the mean values of what we've measured, okay. So what we should expect to measure statistically. And so all of these things have meaning, and you know, playing around with the uncertainties, we get raising and lowering operators of what we could possibly have algebraically. And so if we were to bound these eigenvalues, okay, if we wanted to try bounding these eigenvalues, which logically would come from, you know, if we took the difference, between these guys, this should be equivalent to the axes of the angular momentum that we don't know, or the sum of them, okay? If we took the difference of the of the magnitude of the angular momentum and the axes that we measured it from, this should be equal to the sum of the parts that we don't know, okay? And this operator for a non-negative quantity, okay, its expectation value must be non-negative. So this implies that the expectation value must be non-negative because it's a non-negative quantity, which is restricted by this. And so this implies then for any state that lambda minus the eigenvalue that we had must be bounded above 0, and so it's positive. And so therefore, thus, for a fixed eigenvalue, lambda of the magnitude of the angular momentum vector, or I guess the square of the angular momentum vector, the possible values of m, so possible values of m must be bounded. I hope you see the algebraic and kind of logical elegance of this, and so we can get that exact kind of relation here, which that it must be bounded and squeezed. The eigenvalues must be squeezed between this this m from the this m value that we were talking about, and so that means there must exist. That means there exists a maximum value m max and some in min. Okay, that's basically the logical consequences of the algebra that we've shown, and so this is a lot easier than solving a differential equation for constraining this this eigenbasis or this eigenfunction, and so we want to solve for these now. So let's find these eigenvalues. Now that we know they exist, and they're bounded, which is incredible, and they're related to each other, okay? And so what we need to do now is that if we apply a raising operator to the state with a maximum, with some m max, okay? We want to apply the raising operator, all right? We must get 0. So there is no higher state that we could possibly have. And so what we have here is m max equals 0, okay? And if we act on this equation with the lowering operator, okay? And so if we act on this equation with the lowering operator, what do you think is going to happen? It also has to equal 0. And the reason why is because we can express the lowering and raising operators on each other in terms of their own operators, or in terms of our known operators, okay? So we can just say that this is equal to L squared. If you remember from our definitions, L squared times the square of the angular momentum vector that we measured on the axis that we know, minus the operator itself, okay? And so we can apply this then to this expression here, and so what we'll have is that the square of the angular momentum vector and the square of the angular momentum, the total angular momentum, minus the square of the angular momentum operator in the direction, in the z direction, acting on m max is equal to the eigenvalues minus this maximum eigenvalue here minus this maximum, of course, or the square of it, acting on this, and it should be equal to 0. And so this implies then that the eigenvalue, or lambda, of some m max is m max plus 1. Okay? And we can then rename this m max with a conventional letter. So we'll make this conventional letter L, or capital L, for a total system. Okay, for a total system is capital L. Okay, but for a lower, for just, you know, for this part of the system, we'll call it lowercase l, and what we can have then is that the eigenvalue will be L times L plus 1 for the raising operator, okay, and the lowering operator acting on the raising operator. Similarly, first of all, you would usually do this by means of a differential equation, but instead we found this from just the algebra within this, you know, within quantum mechanics. But if we applied the lowering operator to the minimum state, okay. Of course, if we applied this, I guess let me just erase this. That should also, oh my gosh. This should also equal 0, of course. And then this would then, I'm not going to go through all of it. You can go through the steps again and see if you can do it for yourself. But you should get a result instead of lambda is equal to L times L minus 1, okay? Because it's a lowering operator. And so the quadratic equation, or this quadratic equation here, we'll have two solutions for the L min, okay? And so L min should be equal to L plus 1, which is impossible. Because the reason why this is impossible, because L min should be less than or equal to L max, and L min is equal to minus L. So thus, for a given L, the eigenvalues, the eigenvalues in of the angular momentum operator here range from negative L to positive L. So what this means, okay, so if we were to interpret all of this, what this means is that the ladder operators step between them in integer steps between negative L and L, and so this implies, all of this implies, this work that we've done is that L is minus this is equal to 2L must be an integer. Okay? And therefore the quantum number L, according to our algebra, can be an integer or half integer. So what we found is that the eigenvalues of the squared magnitude of the angular momentum, or the total angular momentum, are capital L times L plus 1, okay, where L is equal to 0, 1/2, 1, and so on, right? Or 3/2, just to be clear, okay? And for a given L, the eigenvalues, say the eigenvalues of M, or sorry, the eigenvalues associated with the position that we measured the angular momentum, or the direction we measured the angular momentum in, they are M is equal to negative L plus 1 ... L minus 1 L. And so we'd say it has a total of 2L plus 1 values. Very, very useful result that is going to come back and help us with our understanding of spin. But we essentially have we've essentially shown and found the eigenvalues. We've derived basically just from pure algebra the angular momentum eigenvalues for this quantum system for the simultaneous eigenfunctions of the of the squared magnitude of the total angular momentum of the system, and some angular momentum that I measured in a particular direction. Okay. Let's look at the eigenfunctions of the angular momentum. Okay. We found the eigenvalues and their structure, but what about the eigenfunctions? So the angular momentum operators depend only on these angles theta and phi, the azimuthal and polar angles, and these they are only these are going to correspond to values that we define as spherical harmonics, and this is going to be denoted usually in the literature we call it y of Ln, okay, of these spherical harmonics are a function of both these angles. Okay, basically this is the eigenfunction. Okay, we're defining this eigenfunction as the spherical harmonics of the angular momentum operators. Okay, and so what we'll have then is this angular momentum operators acting on this YLM, or these spherical harmonics, are going to look, of course, like the form that we derived. Okay, acting on Y, I mean not on psi, acting on Y. Okay, I'm just going to write these angles out so you can really see this clearly. But also, they're going to act, or if we were to act this guy, I keep wanting to write psi, sorry, LM here. If we were to act this measurement in a particular direction, what this is going to look like is this m kind of quantum number here, Lm. We have this. We have these simultaneous eigenfunctions, but they have the same basis or same eigenbasis. Okay. So solving the differential equations using the operators in spherical coordinates, if you solve this, I mean, we're just going to use our basic kind of guess on how to make a good solution to something like this, which is just to separate out the variables. And usually that's typically what most this encompasses a lot of solutions for differential equations, but this phi term here it's going to be a function of little phi, the angle, and they're going to have it's going to be decomposed here for the nth eigenvalues, and this is going to equal basically kind of this normalization constant in front of e to the I m, this quantum number that's associated with this azimuthal kind of angle, and this other guy here are the normalized Legendre polynomials. Okay, they're the Legendre polynomials, and I'll just hopefully you guys can follow this, but the Legendre polynomials are going to look something like this in their full kind of as a whole orthonormal kind of basis. They're going to look like to the -1 of that eigenvalue there, with this 2L plus 1 over 4 pi. I'm sorry, is it 2 pi or 4 pi? I don't remember. I think it's 4 pi. 4 pi, double check me on that, don't take that for certain. Times the difference of those eigenvalues, times the addition of those eigenvalues. We're taking, so basically just the quotient of them, but we'll take them as a factorial, and this is our normalization factor, so we'll just usually refer to this as n, times the Legendre polynomials here, which are just polynomials like x, which is like 1 plus x, you know, x2, x3, so on. It's some expansion of that. But in the x, we have cosines, okay? And of course, they're actually not gonna obey that specific term, term by term, but you have a pattern here, these Legendre polynomials, and that's kind of what this represents, is that expansion times this phase factor again that's implemented by this azimuthal angle, okay? And so for negative m, this is all being multiplied by that, by the way. This is completely a part of this basis, this eigenbasis, okay? And so for negative m, okay, we're gonna have this property where if we take the spherical harmonics, this actually gives us, surprise, the complex conjugate. This gives us the complex conjugate for negative m, because the phase, right? We're shifting this kind of phase factor, and it would receive kind of a negative sign out there. So that's really cool. Now let's talk about the matrix elements of the vectors. Okay, so now that we have our spherical harmonics, what we're going to look at now is for any vector operator. Okay, let's say this is a vector operator, a hat. The commutation relations with the angular momentum operator, they're going to look something like this, where if we have the angular momentum operator with some random matrix, any matrix vector operator, it's going to, of course, we're going to look at this Levi-Civita form again, where it picks out kind of the circular or cyclical kind of logic here, but it's going to be in the this L eigenvalue kind of basis, and so these relations will impose kind of this like strict selection rule. Strict selection rules on the matrix elements of the vector operators, okay, between the angular momentum eigenstates. So these will be, let's say, strict selection rules between angular momentum eigenstates. Okay, and this will look something like a ket vector. That gives us something, and we'll get more into the matrix mechanics. But really now, this is from if you've never seen this before. If I were to have kind of some state, this would be called a bra, and this would be called a ket and bracket, and it has this kind of special quality that if I were to take the complex conjugate of this, well, we'll define this more rigorously, but just think of this as another kind of basis vector, or just a vector in general, okay? Just another way to express it, but in terms of the eigenstates, all right? So if we're going to make a selection rule for L, okay? So let's make a selection rule for L, okay? Let's just do it here. You know what I'm talking about. This is all for selection rules. So the matrix element, so we would say some element, let's say L prime, M prime. If we were to put or fudge this operator, this matrix operator in between vectors here, where these are row vectors and these are column vectors. Okay, so this would be the kets and the bras. We have a bracket, okay, and this makes like a really clean way of representing inner and outer products. It's not hard to see that, but it's basically this is non-zero. This is non-zero if and only if the uncertainty in the total angular momentum is equal to is equal to this guy minus that guy to be equal to 1 plus or minus 1, okay? Let's see. Let's say only if. Okay? So this inner product with this matrix element in here between these two eigenstates would be non-zero only if the uncertainty and the total angular momentum is the difference between them, and the difference between them is equal to 0. Or it would be plus or minus 1. Okay? So basically what we have here is a selection rule for, what we can do is try to make a selection rule for M. So selection rule for M, which is just for a hat z. It's non-zero. So for a z, non-zero only the uncertainty of that eigenvalue, of course, will look something like this. Okay, it should be equal to 0, and for the raising operators, we should have, the other directions times some I, and it does matter which way you pick it out. Non-zero only if the uncertainty in M is plus 1. Okay? And this lowering operator, we just have the minus non-zero only if delta M is equal to -1. Okay? So that's kind of how we select the matrix elements of the vectors in general from an algebraic perspective. Should practice this with some examples, but I think that's pretty important to put in this video. Let's talk about something called the inversion operator. So this inversion operator it's related to the parity of a state. And the reason we would be interested in this is because this inversion operator P changes sign of all spatial coordinates. So there's some symmetry happening here. So if we have P hat acting on psi of r, this should just change the sign of all the coordinates. And if we apply the operator twice, it'll return the original function, of course. So we essentially can just arrive at this, right? And this is not momentum. This is a capital P. Okay, let's make that very clear. Okay, this is a kind of parity or inversion operator, and the square of it has a special property. If you square it, it gives you 1. Okay, and so that means that its energy the eigenvalues then are going to be plus or minus 1, right? And so you can see already why this is interesting, because if we have P, we have the inversion operator returning 1, the state has even parity, right? It has even parity. But if it returns, of course, if it returns the other thing, which is that if P equals -1, the state has odd parity. All right. So for a closed system, let's play around with this. Okay. Well, you might now want to see, like, okay, how do we use this for invariance, right? So if we commute the Hamiltonian with the inversion operator, this means that parity is a conserved quantity. Okay, if we get something to be 0, then we can test this. It's like a test. So test for conserved parity. This is very important for like neutrino physics and stuff, which we won't get to right now, or we won't get to for a while. But for a single particle in a central potential, the parity of a state with orbital angular momentum L is determined. A state with angular momentum. State with angular momentum, or I guess orbital, this would be, we're going to define this L as orbital angular momentum. Okay. L is the orbital angular momentum, and it is determined by how the spherical harmonics transform, basically how they transform to, you know, when we look at these different transformations here that we could apply to the polar coordinates, okay, or the azimuthal coordinates, okay. What happens when we do this, right? This will lead to the rule, then, that the parity, or the inversion should give us, you know, it should be plus the state, or the parity of the state should give us -1 exponentiated to this orbital angular momentum. So the parity of the state is entirely dictated by the orbital angular momentum. That is very important, especially with the spherical harmonics, because this angular momentum eigenvalue is going to tell us everything we need to know in terms of that. So states with even L, so L is even, have even parity. And when it's odd, we have even. No, I'm just kidding. It's odd parity. Okay. All right. For example, if you have a polar vector, like the position operator, let's say r hat, which has odd parity. Hopefully, you can see why that has odd parity. The matrix elements are non-zero, okay? So matrix elements are non-zero only between states of opposite parity. And so this would then require delta L to be odd. Do you see what I'm saying? So the delta L would be required to be odd if in the states of opposite parity, and it's non-zero only between the states of these opposite parities. If this R vector, this radial position vector, or the polar vector, I guess, because it's in polar coordinates, right? So, yeah, I think that's something to try to practice and wrap your brain around. But we're gonna move on. So let's talk about just adding angular momenta. So if we had a system of two particles, let's say angular momentum 1 and angular momentum 2, the total angular momentum, of course, is exactly how you would predict it. We can add them together and it's well defined, and their components, of course, will add simply, okay, for their eigenvalues. And so the rule for adding the magnitudes between them, though, is a little more complex. Okay, so that's not as simple. So if we were given quantum numbers L1 and L2, the possible values that the total angular momentum quantum number L could have, so this would be the total, looks something like L1 minus L2, comma, L1 minus L2 magnitude plus 1, dot, 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 to just L plus 2. Okay, L1 plus L2. So it's like the difference between them. It's hopefully you see this pattern. The difference between both of these guys, for the magnitude, it would be the difference between them, and then the difference between them plus 1, until you get to the sum of them. Do you see what I'm saying? And so this, we call this the Clebsch-Gordon series. Okay, so let's call this Clebsch-Gordon series. So for each resulting value, for each resulting value of L, there is a unique multiplet. Okay, a unique multiplet of 2L plus 1 states. So I guess for all L, there's 2L plus 1 states, and the total. Let's express this a little more compactly. Well, we're starting from the magnitude of them, the difference between them, up to the sum of them. The total number of states is conserved, and so it would be the sum 2L plus 1. And this, of course, if we were to simplify this out, we would have 2L1 plus 1 times 2L2 plus 1. Hopefully you see how I got that. And so the parity then of the combined system would be the product of the parities of the parts. So we can then say that the parity of the combined system is the product of the parities of the parts. And so you can then use that general formula that we use for these orbital angular momentum quantum numbers here. And this gives us an expression for our even and odd parities, which is very nice. So let's combine two spin half particles. Let's try to do that. Let's consider a system of 2 electrons. Okay, 2 electrons. Okay, system of 2 electrons, each with spin angular momentum. Let's say S equals 1/2. And S2 also equals 1/2 because they're both electrons. What are the possible values of total spin? Okay. What are the possible values of the total spin? So what we can first do is use the rule for addition of angular momenta. Okay. So the quantum numbers are L1 equals S1, which is equal to 1/2, and L2 is equal to S2 is equal to 1/2. And the possible values for the total spin quantum number S, we would just apply basically that formula. Okay, so this this is the total. I'm not defining these things very well, but this is the total spin. Okay, what is the total spin? So this would give us the total spin would be S1 minus S2 with the Clebsch-Gordon series to S1 plus S2. Okay? And so we would then have that S would be the magnitude of 1/2 minus 1/2. Okay? Dot, 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 with 1/2 plus 1/2. You see what I'm saying? And so, of course, the total spins then, there's really nothing here. The total spins would just be, would be 0 and 1. Only 0 and 1 can exist. So two spins combine to form a total spin, okay, of S is equal to 1 or S is equal to 0. Okay? So the total spins that are possible between them to combine is this. And let's check the number of states. So if we had S is equal to 1, this is called the triplet state. These are the possible values. The reason it's called a triplet state is because it's the possible values of the z component. It's all the possible values of the z component. M sub s are m sub s -1. They came from, all the lowering and raising operators, and this is a multiplet. This is a multiplet of 2s plus 1, as we described earlier, and so there's 2, and this gives us 3 states. Hopefully you see this algebra and why it works. So 3 states, because we have this original formula for the total spins and the states that we're allowed to be in, and so this is why it's a triplet state. Okay. Now let's look at for s equals 0. This is what we call the singlet state. Okay, and the singlet state, the only possible value of m sub s is 0. Okay, so this is a multiplet of then just basically just 0 plus 1. There's only one state. Okay, so the total number of states would then be 3 plus 1 is equal to 4. Okay, from also including this one too. Okay, this matches the number of states in the uncoupled basis. Okay, think about this. So if you have 2s in the uncoupled basis plus 1, this is 2 1/2. Okay, plus 1 is equal to 2. Okay, so this is for each particle. Okay, and the possible states for little m sub s for the uncoupled basis would give us plus or minus 1/2. So the total number of states or I guess of initial states. Total number of initial states is 2s1 plus 1 times, remember that original formula that we got? This is times, sorry. 2s2 is 1, which is then equal to 2 times 2 is equal to 4. So the number of states then, this implies that the number of states is conserved. Okay? Now, let's work one more problem. Let's look at the scalar product of angular momenta. Okay? So for a system of two spin 1/2 particles, basically just an electron, for the system, find the eigenvalues of the operator S1 dot S2. Okay? For the triplet and singlet states. Basically just the triplet and singlet states are S equals 1, S equals 0. Okay? So we use the relation derived from this law of cosines of operators, so we can just kind of say that if we had this total spin would be the sum of their spins is equal to spin squared to be states that's in here for their angular momenta. We have this where we can then have this expansion out plus 2 this general law of cosines here Okay? And so when we rearrange this for the scalar product, we can have this, we can have the square of this total angular momentum vector here. Okay, like this. And to find the eigenvalues, we can replace the squared angular momentum operators with their eigenvalues, which are, of course, of the form j plus 1, okay? The eigenvalue form, not from, the eigenvalue form, okay? And then S1 would be 1/2, and S2 would also be 1/2, of course, because they're both spin half particles. So the eigenvalues of S1 here, of S1 squared, are S1 plus 1, okay, which would then be equal to 1/2, of course, 1/2 plus 1, which gives us 3/4. Okay. And then the eigenvalues, I guess, of S2, this operator here, would be pretty much the same thing, actually. Just, yeah, it should just be also 3/4, okay, because it's the same kind of spin half particle. So the eigenvalues, we can deduce then, that the eigenvalues of the scalar product operation between both of these will depend on the total spin okay, it depends on S. All right, the total spin. All right, so it depends on what either if we're in a triplet state or if we're in a singlet state. Okay, and really you can think about this as a scalar product operator. Okay, so like, yeah, it's a dot product, but you can, but not really. It's a scalar product operator that depends on the total angular that depends on the total spin. Sorry. Okay, so let's look back. Let's say the triplet state. Let's look at the triplet state. This should give us the eigenvalue of the square of the scalar the eigenvals are S is S plus 1, okay, which is then, of course, 0, 0 plus 1 is equal to 0. Okay, so the eigenvalue for the scalar product between them, between both of these particles, would be actually the expectation value. Okay, because we're working with operators. Remember, we can do this. The expectation value of the particles for the triplet state, okay, is equal to 1. S is equal to 1. We can have 1/2 of 2 minus 3/4 minus 3/4. Remember from that formula that we had, and then this will just be equal to 1/4. Sorry. Okay. All right. That's the eigenvalue there. The eigenvalue of the scalar product. Okay. Of the scalar product operator. Okay, because this is just the scalar product operator. Okay. So we can also do the singlet state here. This one might be a little more straightforward, where we have for this guy the this quantity here is I'm sorry, I got this completely wrong. Please forgive me. This should be 2. No, it should be 1. What am I doing? I substituted in the wrong. I was thinking about the singlet state here. This S here needs to be, but I put 2 in here for some reason. So it should be 1 plus 1. We should have, of course, 1 plus 1 is 2. 2 times 1. Okay, sorry. The eigenvalue of the inner product operator, or of the scalar operator here, is simply going to be just it's going to be 2, okay? And so the eigenvalue of this operator here, where s is equal to 1, you should be able to get this in just 1/4. So this result is correct here for the eigenvalue of the operator, of the scalar product operator. Okay, my bad. And this one, on the other hand, we'll just evaluate it for s is equal to 0, and this will give 1/2 0 minus 3/4 minus 3/4 here, and this should just be 1/2 times that negative 3/4 should be negative 3/4. So basically, this operator here is a key component of spin-spin interaction. Okay, so this encodes spin interaction in the differential equation for the that governs the spherical harmonics, which encodes all the angular momentum operations and eigenvalues and stuff. So the spin-spin interaction relates really, and this gives us the spin-spin interactions for the Hamiltonians. Okay, for the Hamiltonians, such as in the case of hyperfine splitting in the hydrogen atom. And so this is a very useful kind of theory to allow us to essentially explain hyperfine splitting and give us some of these methods of being able to put this in congruency with the natural world, as we observe that electrons really have this kind of spin angular momentum, and we can use the general angular momentum Clebsch-Gordon series to do this, okay, for like m sub s, etc. So yeah, hopefully this was a helpful kind of introduction to spin. We're gonna go a little bit more in depth into the mathematics of spin later with spinners. That's gonna come later though. Next chapter is gonna be on just motion in general in a symmetric field. I'm gonna study that a little bit more in terms of the Schrodinger equation and solving it. But okay, now we have a basic idea of spin and angular momentum, and why it's naturally occurring in the eigenvalues in the simultaneous eigenfunction basis for both the strange fact that we can know the magnitude of the total angular momentum of the system, as well as the angular momentum measured across one particular axis as well. Okay, so thank you so much for watching, and I